Good morning. So we will continue today the lecture number 7, which is about measurement of position. We ended the last lecture studying the sensor, which is typically called metal detector and measures the position of a conductive object. Let's continue now with other types of sensor. And we start with the inductive sensor with variable air gap. In this case, we are back to a sensor which is based on magnetic principle. And again, we have basically an inductor. An inductor where you have a yoke, this yoke here, okay? And there's not a permanent magnet. In this case, the magnetomotive force is created by a coil, which is wound around the yoke. And as you know, the magnetomotive force is given by the product of the number of turns times the current. This coil will generate a magnetic flux, which is following the shape of the yoke, because as you know, the magnetic flux likes to stay in the ferromagnetic material and not to travel through the air. So this flow will continue its journey along this ferromagnetic core. Then there is some air gap, but then again there is some ferromagnetic material. So the flux will arrive here, then it will jump to the other piece of ferromagnetic material, and it will return back, okay? So the flux will rotate this way. It's called with variable air gap because in fact this yoke has a piece which is fixed, okay? So you have this part here which is fixed, and then a part which can be moved to the left or to the right, okay? So when you generate your magnetic flux, this magnetic flux will jump from this yoke to this variable part of the yoke, variable in terms of position, of course, and it will have a reluctance between this ferromagnetic part and this ferromagnetic part given by the air, the amount of air, even if it's not very technical, let's call it like this right now, it has to travel through, okay? As you know, the magnetic flux doesn't like the air, therefore, the larger is the journey, the longer is the journey in the air, the larger will be the reluctance, okay? Again, we can model this yoke, this magnetic yoke with a circuit. We have our coil, which generates a magnetomotive force due to the current that you inject in the coil. So you have an I, which is the magnetomotive force. You have the current, which is, well, sorry, you have the flux. And then you have the reluctance of the ferromagnetic yoke, which is here symbolized by reluctance of yoke. I wrote divided by 2 because, in fact, it's like if you have 2 halves of the ferromagnetic yoke, just to have the circuit symmetrical, but it's not so important. Then you have the reluctance of the movable part, and then you have the reluctance of the air. Again, I remind you that a magnetic circuit is the equivalent of an electric circuit. So instead of generator of voltage, you have a generator of magnetomotive force, Ni. Instead of the current, you have the flux, and instead of the resistance, you have the reluctance. Okay? And then let's solve this circuit. Just to simplify, let's remove the the reluctance of the yoke and the reluctance of the movable part. Why? Because compared to the reluctance of the air, they are very small, because the flux likes to go through ferromagnetic material. So you can consider them negligible. We just simplified. Okay. So you are left with the magnetomotive force, the flux, and the reluctance of the air. Well, twice, because you have this path of the journey in the air and this again when the flux returns back. The reluctance is given by the length of this tube divided by the permeability, in this case the permeability of the air, μ0, and the surface, okay, the cross-section of this tube. Now, let's plug these numbers, let's plug this equation in the general equivalent of the Ohm's law for magnetic circuit. In the Ohm's law, you know that you have the current, which is given by the voltage divided by the resistance. For the equivalent in the magnetic circuit, you have the flux, which is the equivalent of the current, equal magnetomotive force divided by the reluctance. The magnetomotive force will be given by n times the current, where n is the number of turns of the coil. And the reluctance, as I told you, is given by d, if d is this distance here. D is the distance between the movable part and the yoke, divided by μ0, because it's air, so the permeability is the permeability of the air, times the surface, okay? Where the surface is the cross-section. So just imagine that here you have your yoke like this, okay? So you have to imagine that you have this part of air, and of course it's just an ideal case. In real life, it's not, the flux doesn't continue straight from the yoke to the movable part. There are some side effects, but let's simplify. So this is D, and this is the cross section. So let me draw it. Okay. Fine. What does it mean? It means that once you consider this equation for the reluctance, then the flux will be Ni divided by 2d, the distance, times μ0 times S. If you want then to calculate the inductance, you know that the inductance is given by the flux divided by the current, then you have N divided times Phi, the flux divided by current, and then you get N squared divided by 2d, the distance, μ0 S. Now, S, as I told you, if you get the movable part far enough, it's not so constant as you might idealize, but just for the moment, let's consider it as a constant. What we are interested in, interested in now is d, the distance, because now you see that you have an inductor. Okay, you have a simple inductor, and you can measure the inductance. We have studied how to measure the inductance in the previous part of the course. And this inductor is given by an equation where you have the distance here between the yoke and the movable part at the denominator. So if you plot L, the inductance, versus D, the distance, you see that it goes down as 1 over D, okay? Which means that you can simply measure the inductance of this yoke, and you will see that you can recover, you can indirectly measure the distance between the movable part and the yoke. So if you want to measure some some distance, you touch of some object, you touch this object, you attach this movable part to the object whose position you want to measure, and then you measure the inductance. What's the problem here? There's a problem. Can you spot it? Let's see if you are awake this morning. Tell me if you can spot the problem of this sensor. Meanwhile, I will clean the board, so we save some time. Any idea why this sensor is not so nice? What's the problem with this sensor? Come on, it's there, visible, like it's exactly everything we don't want from a sensor. No idea? Come on. Should I promise some points? At least write me if you are alive. So I know that you are not in some other room doing something else. So I want to see within 20 seconds everybody saying I'm alive. Otherwise I know that you are not attending the lecture. Aha, I spotted you. You're not attending the lecture. You're pretending to be connected. Aha. Okay, so I will answer. Okay, I'm alive, so somebody is alive. Evidently there is a larger distance. Okay, evidently there is a large delay, time delay in the broadcasting on YouTube this morning. Okay, everybody is alive. Fine. So if you're alive, tell me why we don't like this sensor. What's the problem of this sensor? That's just tell me. Come on, it's there. Boo, I'm so disappointed. It's non-linear. Come on. Look at the dependence of the output, the inductance versus the distance. Oh, not that much. I exaggerated. It's bloody non-linear. And I explained to you already why we don't like sensors which are non-linear. It's not a matter of discrimination. It's a matter that we want the sensitivity to be the same all over the range that we want to measure the distance, for instance. If we want to measure the distance here, in this range, then if you have a change of resistance here, for this change of resistance, you get this change of the output, okay? And for the same change of distance here, you get basically almost no change of inductance, which is really complicating your life if you want to optimize the reading of the inductance all over the range. Oh, actually, it was here. All over the range that you want to measure, okay? So we need to find a way to make this sensor if not linear, at least slightly better than what we have now. And a very basic principle that you must use whenever you have a sensor which is nonlinear, we will see it many times in this course, is to try to compensate the nonlinearity of your sensor using an opposite nonlinearity. Do you have a sensor which is nonlinear? Exactly here. It goes down with the distance. Well, try to find in your system something which depends on the distance, in this case, and it's also nonlinear. But it is nonlinear with an opposite nonlinearity. Okay? And then you try to compensate them. In this case, there is nothing in the system which is like depending on the distance with an opposite nonlinearity, so we must create it ourselves. So, in this case, we use a double yoke, okay? So, we have our yoke with this variable part, but then we add another yoke here. Now, if we have here D between the first yoke and the movable part, and let's call it D prime, okay? And here we have D double prime for this yoke. You will realize that if the central part, the movable part, goes to the left, D prime decreases, but D double prime increases. And vice versa. If the movable part moves to the right, D double prime increases and D prime decreases. Therefore, they have an opposite behavior. When the inductance of the first yoke will go down, because D prime gets bigger, then the inductance of the second yoke will increase, because if D prime gets bigger, D double prime gets smaller, okay? So what you do, what you obtain is a set of two inductances. L1 from the first yoke, which goes down as we have seen here, and then L2, which increases, which has an opposite behavior. Then we take the difference of them, okay? How do you take the difference of them? Well, you can use, for instance, a bridge. So you have a bridge. Here, it's horizontal. Typically, I've always drawn the bridges vertically. Doesn't change anything here. It's just horizontal. So here you have the voltage source. Here you have a first leg, and we can just put two equal resistances. Then you have, in the second leg, in the upper, I say upper because typically I draw the bridges vertically, okay? In the upper side, we have an impedance, where basically you can consider it almost totally inductive if the frequency is large enough, but of course there is also some resistance. And Z1. And then a second impedance, Z2, composed mainly by the inductance L2. If these two impedances are the same, because the central movable part is in the middle, so D prime and D double prime are identical, then you have two identical inductances, and therefore two identical impedances, and the output voltage will be 0, okay? If then you increase the distance here and decrease the distance here, therefore, you get this impedance bigger than this one, and then these two impedances are not the same, and you have an output voltage, which is not 0 anymore. Okay? Fine. So if you take the difference of these two inductances, you see that first of all, you get 0 output if you are in the middle, okay? Which is something useful because you can set the position in the middle and you have a very small output that you can easily amplify. But most importantly, you have something that, at least here in the middle, appears slightly more linear than the single inductance itself. Of course, this system doesn't make any miracle. You are not actually compensating 1 over d, because mathematically speaking, you are not getting rid totally of the nonlinearity. So when you go at very large or very small distance, or very large distances from the middle, either to the right or to the right, at the extremes, in other words, still the system is nonlinear. Okay, so but at least here in the middle you gain something in linearity. Now, let's if there is any question, just drop it there in the comment section. Okay. Another sensor is the linear variable differential transformer, LVDT. Okay. So transformer, you know what is a transformer. It works only in AC, so definitely we know that from basic courses of electrotechnics. Typically, a transformer has one primary coil and one secondary coil. So the primary coil generates the flux, and the secondary coil picks up the flux. And since we are in AC, there will be a voltage induced in the secondary coil, which is proportional to the flux that the secondary coil receives. In this case, we have two secondary coils. Here, we have a first coil, a main coil in the middle, where you inject some AC current, which generates the magnetic flux, and it's in the center. Then, you have a ferromagnetic core, which brings the flux to the secondary coils, one on the top and one in the bottom. This core can be moved, okay? So you have your coil, and here you have this core, which can be moved, is movable. Why? Because it is attached to what we want to measure the position of, okay? So let's say that we want to measure the position of an object. We attach a rod, which is connected to the magnetic core inside the LVDT, and as you move it inside and outside, this ferromagnetic core will bring the magnetic flux where the core goes. So if you bring the ferromagnetic core on the top, it will bring all the flux on the top to the secondary coil located at the top of the primary coil. So in this case, all the magnetic flux goes to the top, and almost no flux goes in the bottom. Okay? So the voltage induced at the terminations of the secondary coil at the top will be large, and the voltage induced at the secondary coil in the bottom will be almost nothing. So you can plot the dependence of this voltage as from the position as seen here in this graph. If you bring, on the other hand, if you bring down the ferromagnetic core on the bottom, then the voltage will be, the flux will go mainly to the bottom, and therefore the main voltage generated will be at the secondary coil and the bottom, because most of the flux goes down at the bottom. So now you understand which is the role of the ferromagnetic core. Ferromagnetic core has the purpose to lead the flux wherever we want to bring the flux. Now, this sketch is probably oversimplified. Keep in mind that if you have a primary coil here and the two secondary coils, okay, here. Now you bring the current here. Then the flux, if you put your ferromagnetic core here, there I simplified that all the flux goes here, okay? But of course, here you have some flux generated by these turns, okay? So it will deform the magnetic field, but it will not be symmetric with the respect of the ferromagnetic core. It's a simplification. So there will be also some voltage on the top. But the purpose of the ferromagnetic core is this, to bring the flux where you want. So when you generate some flux, when you generate, let me erase this. Let's see if I can make a decent drawing of what is going on. If you have this ferromagnetic core here, well, the flux, instead of going like this, well, it will be drawn here, like it will be deformed to flow through the ferromagnetic core, okay? And here it will continue this way. If you take down now the difference between these two coils, you get something which is, again, I oversimplified here, but it's kind of linear in the middle, at least, of the sensor. It's not totally linear because when you arrive at the end, again, this trick doesn't work anymore. This trick of the compensation. But the method, the principle is always the same. What you're doing is to take one non-linearity, because if you observe one dependence, or if you observe the dependence of one voltage from the position, you get something which is nonlinear. Then you observe the same dependence of the secondary, the same dependence of the secondary coil on the bottom, and again you get something nonlinear. But as I told you before, when you have something nonlinear, you must find in the system another nonlinearity which can compensate the first nonlinearity. In this case, we have one nonlinearity in the first place, and then we must find another nonlinearity opposite to the first one, so that we, taking the difference, we can get rid of the nonlinearity, at least to some extent. In this case, how can we achieve a second nonlinearity opposite to the first one? We add another coil. Where? In the opposite position. So that if you increase the voltage on one side, because you bring the flux on the first coil, you get a nonlinearity on the first coil, but it will decrease on the secondary coil on the bottom, so you have an opposite nonlinearity. The trick is always the same. You have one nonlinearity, fine, try to find another nonlinearity opposite to the first one. If there is not anything in the system to do so, well, simply try to create it yourself. In the previous example, we created it by adding another yoke where the distance decreases here and increases here. So you have opposite behavior. In the LVDT, it's the same. The flux increases non-linearly in the first coil, but we add another coil where it decreases non-linearly with opposite nonlinearity. Okay? Always try to keep in mind this principle. So this is what is schematic. So you have a first part of the circuit where you create a flux with the primary coil, then you have two secondary coils, and as you see, they are connected in anti-series. So at the output here you get V2 prime minus V2 double prime. Of course, you don't typically need to do this by yourself. There are some circuits which already do everything for you, mainly because these are very, very common sensors. They are very, very commonly used, so you don't expect people every time they need to use an LVDT to build the circuit for an LVDT. There is market enough to create circuits, to create ICs which automatically do everything for you. So like analog device has this circuit where inside you have already a voltage reference which creates then, thanks to an oscillator, the current. So you can connect the first coil to the oscillator. Then you get the output, you connect the output of the secondary coil, and there is a demodulator which allows you to extract the component at the same frequency of the oscillator and transform it into a DC voltage. So at the output, you obtain directly a DC voltage which corresponds to the amplitude of the difference of the voltages, okay? So you take these voltages, you connect in anti-series, you have this output voltage which is at the same frequency of the input current, and then you must demodulate it, and this circuit does the demodulation by yourself. This is quite also interesting because one might think, okay, why don't I simply measure peak-to-peak voltage? Well, there are two main reasons why you cannot measure directly the peak-to-peak voltage as an output, okay? The first reason is that you cannot distinguish negative voltage from the positive ones. But the second main problem is that then you are depending also on other frequencies. In the output, you will have not only a component of the voltage due to the magnetic flux generated by the first coil. There will be any other sort of frequency due to disturbances, due to voltages induced there by other sources of magnetic fields. But they don't bring any signal, they're just noise. It's just some magnetic flux which sneaks inside and will cause some voltage at the output. So you want to get rid of these components of the output voltage. And how can you distinguish between these values, between the values of the voltage which are bringing signal, and there are components of the voltage which do not bring any signal but they are noise? You watch the number plate. The number plate of the signal in this case is the frequency. If you excite here at frequency F1, you know that the output here must be at F1. And if you don't see, if you see a voltage which has a different frequency, you know it's not given by the flux itself, but it must be noise induced by something else. So by using the modulation, what you do is to extract from the output voltage only the component of the voltage at that particular frequency. This is and therefore you get rid of all the other components. This is a principle always used when you are working in AC, because it allows you to distinguish between different sources of voltages. You can consider the frequency as a number plate of a signal, okay? Fine. Inductance. Aha, this is funny. Any questions so far? If you have any questions, don't hesitate to type it in the MS Teams, okay? Inductance. Let's start with the planar coil, which for someone might sound weird, but it's nothing else than a coil just laid down on the plane, okay? So just imagine to have a regular coil. Now this is going to be a little bit difficult because making this kind of drawing is not easy, so I will challenge my drawing skills. Just imagine that you have a coil and by accident is not round but is squared, okay? And now let's flip down each of these turns, okay? So if I have the first here, it will be like this. Then you this one. And so on, okay? So just imagine that. Now I will try maybe to show it with my fingers, okay? I don't know if this is gonna work, if the resolution is large enough, or maybe I should show it like this, that you have a dark background, okay? So just imagine that you have two coils, one coil with two turns like this, okay? And then you flip this down, okay? Maybe I should show it like this. Okay? And now it's difficult with my fingers. Okay, something like this. I'm not sure if you can see it. Maybe it's better if you see what happens directly on the current, from the point of view of the current, which generates a magnetic flux. Let's say that we insert a current in the coil. So it goes this direction here, returns back, goes there, returns back, and so on. Now, what happens to the magnetic field? You know that you have a current which enters in a wire, so it will create, according to the right-hand rule, a magnetic field which is surrounding the wire. So the current in the first wire will generate a clockwise magnetic field. When it returns back, it will have opposite directions, so it will create a counterclockwise magnetic field. So when you watch in the middle, you have in both cases magnetic fields pointing down, okay? So therefore the magnetic field in the center here will point down. When you watch the second turn, you will see that the first current coming toward us, it will be counterclockwise. The current going there will be clockwise. And in both cases, if you watch in the middle, the current generate a magnetic field pointing to the top, okay? And so on. For each turn of this planar coil, we have a magnetic field pointing to the bottom, top, and so on. Now, we put another coil above this first coil, okay? And of course, it will feel the magnetic field. Of course, I'm talking about AC magnetic field. It will receive the magnetic flux generated by the first coil. And of course, it will have, in the first turn, it will feel magnetic field pointing down. In the second turn, pointing up, pointing down, up, down, okay? Now, in this case, the flux is maximum. And this might be a little bit misleading because you see that you have different turns where you have positive and negative flux, positive and negative flux, positive and negative flux. So you might expect, well, in this case we have an odd number of turns, but that's not the problem. You might think that this flux received in the first turn pointing down will cancel the flux in the second turn pointing up. But that's not actually true. Why? Because let's say here we have pointing down and here pointing up, okay? What happens when you ideally rotate the second turn on the first one, okay? Just imagine that you can magically take the second turn no, this is not okay. And you can flip it, okay? So that this is the magnetic flux. Okay? I don't know if the drawing is clear enough, but just think that, again, if you were here, it would be very easy to show with my fingers. Just think that you have here the first turn and the second turn, and you rotate it, okay? Now, the magnetic field and the second turn, which points up, if you rotate the turn, will point down, okay? So when you finish the rotation, this will be here, and both arrows will point down, okay? So you take the second turn here, you rotate it on the first one, and the arrow which was pointing up now points down. If you don't trust me, what you can do is to take some paper, like draw this path corresponding to the copper carrying the current on some paper, and then you can see that folding it on one coil, one traditional linear coil, not cylindrical because it's not a cylinder, but that is not important. Then you will see that you have all the arrows pointing down, okay? I hope it's clear. However, if you move the secondary coil halfway between the turns, like as shown here, then the flux is really zero. Why? Well, because each turn, for instance, this one of the secondary coil, will receive half flux, which is pointing up, and half flux, which is pointing down. The second, again, half flux on the down, half flux up, and so on. So, since you put the secondary coil halfway, each turn receives zero. And then, of course, the sum of the flux of all the turns will be zero. So, in this case, you get zero flux. Not in this one. This gives you maximum flux. So be careful, because this is a typical situation where you see up, down, up, down, up, down, say, okay, the sum is zero. Oh, here the sum is maximum. Here the flux is zero. So what you do, if you observe the voltage induced in the secondary coil, this will be proportional to the flux that the secondary coil receives, the total flux. And of course, because the voltage is proportional to the derivative of the flux, and the frequency is always the same. So it's not a matter of frequency, but it's a matter of amplitude. Okay? If the flux increases, also the derivative increases, not because of the rate of change, but because simply you have a constant in front of the derivative. Fine. So if you watch at the amplitude of the voltage versus the distance, you find out that you have the maximum flux here on the top, which corresponds to this configuration when the secondary coil is facing symmetrically the first coil, the generating coil, and you have 0 flux here. Okay. Now let's be careful, because when when students see some sign, they think always it's a sign on time. This is not a sign in time. This is a sign in distance. Okay. So now we have here a distance, and here you have this behavior. What does it mean? It doesn't mean that this is the voltage in time. This is the amplitude of the voltage. Here, it means that on a scope, we see a large voltage. Here, it means that we will see on the scope a small voltage. Here, on the scope, this is the time. This is the time. Here is the time. We see nothing. What happens here? What is this value? Negative amplitude. Well, it simply means that the phase is reversed. You still have large voltage, but it's shifted by 180 degrees, okay? So this is not a sign in time, it's a sign in distance, and each point here represents the amplitude of the voltage in time, okay? There is a problem. Let's say that you are here at the top. Then the inductance changes position. You see a drop in the voltage, for instance, this voltage here, and you don't know if the system went to the left or to the right. You observe only that the voltage decreases. So if you watch only the amplitude of the voltage itself, you have no means to understand if your system went to the left or to the right. Of course, you could say, well, just watch it. Yeah, but therefore, you have another tool of measurement. You need another device which measures optically, in this case your eyes, if the device went to the left or to the right. You want a device which itself, without anything else, tells you if the system went to the left or to the right. How can we solve this problem? Here we find another important principle of sensors. We will see it here, but we will see it also for many other sensors. When you have a problem like this, and you don't know if you went to the right or to the left, because the function is symmetrical, then you have to add another coil, in this case, which is shifted by a quarter of the period. In this case, we have a period which corresponds to 2 turns of the primary coil, because here you have the flux going up, flux going down, and then it repeats up, down. So if you watch the first coil, each 2 turns, you have the same behavior of the magnetic field. So 1/4 of the period corresponds to half of a turn. So we add a secondary coil, another secondary coil, which is shifted by half of the period with respect of the first one. And therefore, also the response, the amplitude of the voltage versus the distance, will be shifted by a quarter of period. Now, if you are at the maximum voltage here at the first coil, and you see that the voltage decreases, now you can distinguish if you went to the left or to the right. It's enough to watch the voltage at the other secondary coil, at the second secondary coil, and if you went to the left, the secondary coil will have a large voltage. If you went to the right, the second secondary coil will have almost zero voltage. Okay? So you can distinguish between these two values of the first coil, which by themselves they are absolutely identical. The voltage on the coil 1 is absolutely identical, but the voltage on the coil 2 is not. So it's enough to watch at the secondary coil. And of course, you have the same issue with the secondary coil 2, which will have symmetry, but it will be, but the first coil will not have symmetry. So if you want, you have sine, cosine, and you can get the tangent out of that. And then you don't have this problem anymore. Another sensor of position, now this principle really is very important always. When 2 is not enough, go for 3. Okay? So instead of having only primary and secondary coil, add another coil shifted by a quarter of period, and you get rid of this problem by watching the other secondary coil. We'll meet this principle again several times in this course. Capacitive sensors. You know what is a capacitor? You have two metallic plates. You know that the capacitance is given by epsilon times the surface divided by the distance. Now, if you change the surface, simply because you take the two faces and you move them away, then the equivalent surface decreases and you get a different value of capacitance. This can be done linearly, or like also for angles, you have these capacitors where you have like circular or semicircular faces like this. Then you have other electrode like this, and you can rotate the angle of the relative angle between the first and the second plate of an angle alpha, and the equivalent area they are facing is the one where the electrodes, the plates overlapped. Okay. Again, we have the same problem, or another alternative is to move them with a distance, as well as we did for the inductive sensor. You can move the distance between the plates, and again, we obtain a change of capacitance. Again, we have the same problem, because here the capacitance depends on the distance as 1 over the distance. So we have a function which is nonlinear. So guess what? What should we do when we have something which is nonlinear? Yes, we have to find an opposite nonlinearity. Okay? An opposite nonlinearity, in this case, if one phase gets closer, if two phases get closer, then you need another capacitance where the distance between the phases gets larger. Okay? So what you do is, again, to have two plates here, which are fixed, the external ones, and the plate in the middle, which can move. So if the central plate goes to the left, you will have the capacity C1 increasing and the capacity 2 decreasing, and vice versa. If the plate, central plate moves to the right, the capacity C2 increases and the capacity C1 decreases. And as usual, we take the difference to get something slightly more linear. Okay? There are other sensors based on capacity which are proximity sensors. Typically, a capacitor is shown as two plates facing each other. But that's not the only way to make a capacitor. For instance, you can have concentrical capacitor, where the two electrodes are composed of one central rod and one external ring. Now, I plot only the electric field on one plane, but of course it's 360 degrees. So you have the electric field which goes from the central rod to the external ring. What happens when you put a material with a different permittivity than the air in the middle? You have an epsilon, which is not the same of the air, and for instance you have plastic, any other type of material, and you can identify the presence of this object in front of the sensor simply because the capacity will change. Okay? This is particularly used for materials which are not conductive or magnetic, so you cannot use other principles we have seen before where we make use of magnetic field, or for instance for metal detectors where you can measure only conductive materials because you need eddy currents. So if you have insulating material, the best way is to use capacitive effect. Okay, so you play with the fact that they have a different epsilon, okay, than the air. Now let's go to optical sensor. The very first basic one is composed of a disk, simply, where you have at the outer shell a set of holes, okay, at fixed angle distance. Then you have a source of light and a detector of light. If the detector is in front of a part of the wheel which has no hole, the light will be blocked and it will sense no light. If the detector is in front of a hole, it will detect the light. Okay, so you can detect the position, the angular position of the wheel by watching at the state of the detector of light. Very simple. In this case, we are talking about incremental optical sensor. Why incremental? Because by itself, you don't know the angle of the sensor, the absolute value of the angle of the wheel. Why? Well, because if you have your sensor facing let's say that we have this wheel here, and you have a lot of holes all around the circumference of this wheel. Okay? Very quick drawing. If your detector is in front here and it receives the light in front of this hole number 1, or if it's in front of the hole number 4, okay, let's say this is number 4, you cannot distinguish this situation. Okay, simply you see a hole and the light passes through the hole, so you detect the light. So if you want to know the absolute angle of this sensor, you have to count how many pulses you receive. You start from a position where you know you have 0, so you press a button in the counter, you 0 the counter, and then every time you get a pulse, you increment. Let's say that you have each angle, each hole is, I don't know, 10 degrees. Each time you have a pulse, you count more, 10 degrees more, 10 degrees more, 10 degrees more. After 3 pulses, you know that you moved by 30 degrees, okay? And so on. What's the problem? The problem is that if you are in a condition like this where you have no light, okay, and then you get a pulse, you don't necessarily know that you move by 10 degrees clockwise or 10 degrees counterclockwise, which means negative 10 degrees. So you don't know if you have to increment, if you have to increase your counter by plus 10 degrees or minus 10 degrees. Because if you're here in the center where you have no light and you move to the left or to the right, well, in this case, clockwise or counterclockwise, still from the condition of no light, you get to the condition of light. So how can you distinguish if you went clockwise and counterclockwise? You see, this is not a trivial problem because you might have a wheel which moves 10 degrees to the clockwise, 10 degrees counterclockwise, clockwise, counterclockwise, clockwise, counterclockwise. It's always moving one step left, one step clockwise, one step counterclockwise. So at the end of the day, it's always there, plus minus those 10 degrees. And you can have a wheel which moves always in one direction. Every pulse corresponds to 10 degrees continuously in one direction. From the point of view of the output of your sensor, they will both give you a set of pulses. No light, light, no light, light, no light, light. But in the first case, this set of pulses will correspond to a wheel which goes back and forward all the time and is still there. In the second case, the same set of pulses gives you a wheel which continuously rotates in one direction. So how can you distinguish these two different, completely different situations? Well, it's very simple. What happens if one is not enough, one gear is not enough? You add another one. Shift it, as I told you, by a quarter of period. So here, you create a second wheel with the same number of holes. And in the second set of holes, you see that these holes are shifted by a quarter of period. So you can see it here. Maybe in this 3D sketch is not so visible. Maybe you can see it here, that they are shifted by a quarter of period. Maybe you can see it better here. So you have two sets of holes, and where there is the yellow color here, you have the light. When there is the gray, there is no light. So basically, you have sort of binary code, okay? 0, 0, 1, 0, 1, 1, 0, 1. And again, in this case, you know that if you are in the condition of no light, okay, and you move clockwise, then you get a pulse, and you get here the second wheel which has light. If you move from a condition of no light in the first wheel to a condition of light in the second, still in the first wheel, then you observe the secondary set of holes, and you see that there is no light, okay? So here you see that you can distinguish between the movement clockwise or counterclockwise simply observing the secondary set of holes, okay? This could be rotative, but could be also linear, okay? So you could have the same principle with some slits created not on a gear, but on a linear movement, on a linear plate, but the principle is exactly the same, okay? If you don't want to use a counter, what you can do is to use an encoder. In this case, we measure the absolute value of the angle. How do you do it? You have multiple rings on your wheel, and in this case, we have 5 rings. Oops, 1, 2, 3, 4, 5. Each of them represents a bit of this digital output, okay? And as you see, the outer ring changes from light or no light condition every step. This which corresponds to the LSB. Okay, so it's the last digit of the binary number. So it's like the last digit which went to 0, 1, 0, 1, 0, 1. Then the second ring, as you see, has a double periodicity. So it changes every two steps of the outer ring. And so on. Every step you change and you have periodicity which is twice as big. Until you arrive to the central ring, that it has only 2 steps, which correspond, of course, to the MSB, the most significant bit. If you write down all these numbers in binary from 0 to 0, 1, 1, 1, 1, 1, okay, so 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, you see that progressively the LSB changes always 0, 1, 0, 1, 0, 1, 0, 1, and the MSB changes 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, okay? So it has this different periodicity. Another sensor of position, let me see how much time I still have. Oh, shouldn't be that bad. Is a triangular optical sensor. It's based on triangulation, which means that you have a laser pointing on a target where you have a reflective object. This light is reflected, and according to the target, is reflected in a different position of the sensor. Here there is some lens to focus, of course. So if the target is here, it's reflected on this line, and it hits the sensor here. If the target is more distant, for instance here, it will be bouncing back here, and therefore it is received by the detector in this position, and according to the position where the light arrives, I have a different response from the sensor. Okay. Now we have studied a lot of sensors which are very efficient in measuring, let's say, large distances. But what happens if we want to measure very small distances? Well, one of the systems is the so-called interferometer, and it's based on this principle. You have a laser, and then you use a beam splitter to divide the laser into beams, okay? Then you have a fixed mirror on the top, which reflects back the first beam to the detector. Be aware that the beam splitter divides only if the beam arrives in this direction. So when it returns back, it can go through without any problem. Okay. Now, the detector, therefore, will receive the first beam, which comes from the laser. It's reflected up by the beam splitter, and then is reflected by the fixed mirror and returns back. Then you have a movable mirror. So the second beam arrives to the movable mirror, it's reflected back and goes to the detector. When the two beams have the same, or let's put it this way, when the two mirrors, the fixed and the movable mirror, are at the same distance from the beam splitter, then the path of the first beam, which goes to the fixed mirror and returns to and goes back to the detector, and the path of the second beam, which goes through to the movable mirror and goes to the detector, is the same. So they have to go through the same path, they have the same speed, they meet at the same time. Okay? Therefore, they could have a different amplitude, for instance, and when they meet together, they are in phase. So they sum up together, and at the detector, you see the laser with an amplitude given by the sum of these two beams reflected back. What happens if you move, however, the movable mirror? You cannot move the fixed one because it's fixed. So you move only the movable mirror. And then the movable mirror is not at the same distance. Let's say it's at a larger distance. So the light must take slightly more time to go there and return back, because it has to travel for slightly more distance, okay? So by the time it arrives at the detector, it's late, because the first beam already arrived there. The first beam had to travel less distance. Now the movable, the other beam, which goes to the movable mirror, has to travel slightly more distance, a little bit more there, and a little bit more back, okay? And therefore, when it arrives late. It arrives later than the first beam. And therefore, they are not in phase anymore. By being not in phase, you see that the sum of them now is lower, until you arrive to these two beams which are not in phase anymore. If, for instance, the movable mirror here is the condition where the distance is 0, okay? So this is the 0 condition point. I move it by a distance, let's say key, and key is lambda quarter, where lambda is the wavelength of the laser, okay? So it has to travel lambda quarter there, more, and lambda quarter back more. So there is this extra path there and extra path back. So total you have lambda half of the wavelength, okay? So you have some lambda quarter more there and lambda quarter extra returning back. So the total is lambda half, so half of the wavelength, and therefore when it will be back at the detector, you will see that it's a quarter, half of the wavelength late, which means that it's shifted and it's in antiphase with respect of the first beam. Therefore, you get the two beams in antiphase and you get the minimum light. So what you do is to observe the amount of light at the detector, and you know that when the light is minimum, it means that these two beams are shifted by half of the wavelength, okay? Again, this system can give you a measurement of distance within the wavelength of the light that you are using. If you use a laser at, I don't know, 500, I don't know, nanometers, or 680 nanometers, you can measure the intensity of light changing and being maximum at 0 and minimum at half of that wavelength. So if you use 680, you have 300 quarters nanometers. And then it will repeat. If you shift it again, you get maximum light, minimum light, maximum light, minimum light, every time if the position of the movable mirror is at the multiple of 380 nanometers, okay? So there is a periodicity which is given by this wavelength of the laser that you are using, okay? Which means that once you start again from a position of 0, then you can measure these distances. If you want to measure distances larger than the wavelength, what you have to do is to start from a position of 0, then 0 your counter, and every time you get a pulse, or every time you get a condition from 0 to maximum light, you know that you moved by half of the wavelength, okay? So 340 nanometers if you're using 680 nanometers light. Then the light goes back down and back up, and you have another 340 nanometers, and so on, okay? Every time you see the change of light from minimum to maximum, you know that you moved by 340 nanometers. That is half of the wavelength, and so on. Of course, this doesn't mean that you can measure only changes of 340 nanometers. You can measure clearly even lower lower distances. How? It's very simple. You have to be able to change. You have to be able to measure the difference in light from a light which is this small to a light which is this big. If you change the light by an amount of that you can detect using the detector, then you are able to measure the distance which caused that change of light, okay? So it doesn't mean that you can measure only steps of 340 nanometers. If you're able to see, if you're able to appreciate, if you're able to observe and measure a change of light smaller than that, fine. Let's talk about resistance. So now we move back from measurement of very small distances to bigger distances. Let's go to resistive sensors of distance, which is nothing else than potentiometers, typically linear potentiometers. I'm pretty sure everybody worked with potentiometer. Simply, it's a variable resistor where you have you can connect simply an output, a voltage generator on the resistor. Then you have a central electrode, and the resistance that you have at the output depends on the position of the electrode. And of course, you just connect a voltmeter, and you get a value of voltage proportional to the resistance, and therefore proportional to the position of the electrode. What is the problem? As you know, the voltmeter ideally has infinite input impedance, but if you have a bad voltmeter with a low input resistance, then you must consider that here you have a resistance, a finite resistance, which loads this circuit. So what you have here is not only R2 proportional to the position, but you have R2 proportional to the position in parallel with RZ, okay? So you can substitute in this circuit R2 with R2 in parallel with RZ. Now, R2 is proportional to the position, but RZ is not proportional to the position. Therefore, their parallel will not be proportional to the position anymore. You lose linearity. And this is something you don't want. So, in order to, oh, by the way, if you don't trust me, just calculate this, this parallel. Take this RZ as a constant. R2, you put it there as a function, linear function of a position. Let's call it P. You make your calculation, then you see that it's not linear anymore. You can even plot it, make some example. This problem is given by the fact that here we have a non-infinite input resistance of the voltmeter. How can we solve this problem? We have already seen it. We can use a voltage follower where we basically replicate the voltage in the input to the output, but the input impedance is almost infinite because we absorb no current, okay? So we are not absorbing any current, we are not loading the circuit, and therefore we don't affect, we don't load the circuit, we don't change the linearity of the system, okay? So never forget that if your circuit absorbs some current, you have to use some operation amplifier in voltage follower, okay? This is a type of potentiometer, just to show how it looks like with this central rod that you can attach with some screws to the object whose position you want to measure. Let's talk now about accelerometers. What if you want to measure the acceleration of an object? You can definitely measure the position and take the second derivative of the acceleration, which is the second derivative of the position, which is the acceleration. But it's not so convenient. It's much better to use a physical principle where you know the output quantity depends on the acceleration. In this case, we know that the force on a mass is equal to the mass itself times the acceleration. So what we do is to take a seismic mass and we expose the mass to acceleration, and as a result we have a force on the mass which is proportional to the acceleration, okay? So we don't measure the position and then calculate the second derivative, but we directly make use of physics. We find a physics law where the output is proportional to the acceleration, and then we measure that quantity which depends on which is linearly proportional to the acceleration. How does it work? So we have a seismic mass which is suspended with four this connection to some fixed point. So these squares here represent some fixed point. And if you apply a force, you can, if you apply an acceleration, you obtain a force, and the mass can move as a result of this force. So what you measure is not even force, is the displacement caused by the force, caused by the acceleration. And not even that, because you don't directly measure the displacement. What you have here is some capacitive sensor of displacement, the same that we saw before. You remember, you have two external plates which are fixed and one in the middle, and then you take the difference between the two capacitances, and in order to compensate the nonlinearity. The capacity depends as one is proportional to 1 over the distance between the two electrodes. So when the central electrode gets closer to to the electrode on the right, you get larger capacity on the right, but larger on the left, lower on the left, and vice versa. So in this case, for instance, we have the central electrode, which is closer to the electrode, to the fixed electrode on the right. Therefore, this capacity will be bigger than this one. So at the end of the day, what we measure is the difference of these two capacitances, which is a measurement of this displacement, which is a measurement of the force, which is a measurement of an acceleration, okay? They are called MEMS. MEMS stands for microelectrical mechanical system, because you can build them very, very small. Okay, now this looks big, but typically you can build them so small that you can embed them in any type of IC. Typically that's what you have on mobile phone. So when you wonder why the mobile phone knows if it's vertical or horizontal, it's not just that they watch at your face and then they decide if it's flipped down. In reality, they have a sensor of acceleration, in this case, gravity. So when you have your phone like this, they feel a gravity in this direction, and in this case, you feel it in the opposite direction, okay? So they sense a force, the gravity, and there is a displacement on this seismic mass, and then you read the difference of capacitances. And really, you can make them at micrometric scale, so they can embed it without any problem in this kind of device. Now, it seems I have only 3 minutes, and it's not enough to finish the sensor of vibration, so I will finish here, and don't be scared about this equation. It's easier than you think. So next week, I will continue from here, and then we will continue with lecture number 8, okay? Is there any question? I could do it now, but I need to explain something. I don't want to rush this explanation, so I want to take my time to do it, okay? If there's no question, enjoy your weekend, and as usual, stay safe.